Hello everyone, welcome to the next problem solving session for the NPTEL course Novel Technologies for Food Processing and Shelf Life Extension. In this particular week, we'll be solving problems related to week 10 syllabus. So, if you guys have any doubts throughout the problem solving session that you want me to repeat any question, also you can post it in the group chat or unmute yourself. If you want to answer any question also, you can do the same. So, we'll proceed with the first question. Which of the following is most acceptable and cost-effective commercial method of ozone generation? A. You have electrolytic method. B. Corona discharge method. C. Photochemical method. And D. Radiochemical method. So, which among these four is the most common and the cost-effective commercial method for ozone generation? Yeah, so the answer is Corona discharge method. The reason why we need a very cost effective and acceptable commercial method for ozone generation is that ozone is very unstable. It can combine back to form molecular oxygen or so. So if that is the case, then we cannot store ozone anywhere. It has to be generated at that particular moment by the most effective method that you can figure out. So, amongst all the four methods are commercial method of ozone generation, but then the corona discharge method is the most acceptable and cost-effective commercial method of ozone generation. So, just to give a small brief introduction to corona discharge method. So, in a corona discharge method, you have two electrodes. One is the anode high voltage electrode, and the other one is the ground electrode. So what happens is that these electrodes are connected to a transformer that gives it an additional voltage to the electrodes. And between these electrodes, you have a dielectric, and between the dielectric and the ground electrode, you will have as much as pure air, dust-free air that is passed through the electrodes. So what happens is that a spark is generated because from the high voltage electrode, and this spark is kind of uniformly distributed throughout because of the dielectric present. So a spark generally, if you don't have a dielectric, that spark will happen only at a particular position within the air molecules. But then if you have a dielectric, that spark will be distributed across the entire region between the electrodes. So you'll have a more uniform distribution of the spark that you're giving, and because of this spark, the molecular oxygen will generate O first. From O2 will change to O, and that O atom will combine with again molecular oxygen to create ozone. So if you have a very uniform distribution of your spark, also known as the corona, so if you have a uniform distribution, then more amount of ozone can be synthesized, which is why it is most effective, cost effective method. So because of the dielectric, there is a distribution of the spark. This will create more ozone, and hence this is the most effective commercial method for ozone generation. So answer is B. So if any part of the question needs to be repeated, kindly let me know. Question 2. So in this problem solving session, we'll discuss a few problems related to silos. That is, your grains will be stored in a lot of silos or silos. So in there you need to maintain certain pressure, certain temperature and everything to prevent any sort of infestation, any mold growth or any damage to the seeds. So according to that, we have to design silos in such a way that it is able to withstand your needs of grain storage. So we'll be discussing a few problems related to this silo design. I'm not sure if this is present in the, I don't think this is present in the lectures as such, but then it's kind of commonly asked in the assignment questions in the previous years and all. So reading the question, a silo of 1.82 meters in diameter and 20-meter high is made of mild steel sheet. Corn is stored into it up to a height of 15.24 meters. Compute the vertical pressure in kilonewton per meter square at the base of the silo. Given the bulk density of corn is 700 kg per meter cube, The angle of intergrain friction is 30 degrees, and the coefficient of friction between the grain and the mild steel is 0.42. So the ratio of lateral to vertical pressure is also given as 0.33. So what happens is you have a vertical silos with a certain diameter and a height where you will store your corn. So because you are storing corn up to some around 15.24 meters, there will be some sort of vertical pressure happening because of the height of the corn at the base of the silos. So because of the height, that is 15.24 meter height of corn, there will be pressure acting at the base of the silos, and based on that, your silos has to be strong enough to withstand that amount of pressure that is because of the corn. So that is something that we need to calculate here. What is the vertical pressure at the base of the silos? What we need to calculate. So we are given here the density of the corn, we are given the dimensions of the silos, and we have something known as the angle of intergrain friction. So what happens is when your grains are present or heaped inside the loaded into the silos, they often undergo some kind of friction between the grains because they have a sliding capacity. So if you pour grains, it will start sliding. Because of that, they often have friction between the grain particles, and this friction between the grain particles is given by this friction angle, which is 30 degrees. And the coefficient, there is also friction between the grain and the steel sheet, that is the silos. So between the grains also you have friction, and between the grain and the silos also you will have friction. So all those will kind of influence your pressure that is acting on the base of the silos. So given the diameter of the silos is 1.82 meters, height of the silo is 20 meters, bulk density given as 700 kg per meter cube, the angle of friction between the grains, which is known as theta, is given as 30 degrees, and the coefficient of wall friction, which is given as mu, is 0.42, and the ratio of the lateral to vertical pressure is 0.33. So when you're dealing with grains in a silos, there are two kinds of pressure that is acting on the grains. One is the lateral pressure, that is the horizontal pressure. The other one is the vertical pressure. So the ratio between the lateral and the vertical pressure is given as 0.33. So first, before, there are multiple formulas that are used for designing the silos. One formula we'll discuss here. The rest of the formulas we'll discuss in the coming up questions. So first thing, when you're dealing with design of a silo, you need to figure out what kind of a silo are we looking at. So first, we need to calculate the type of the bin or the silos using the relation between H and R, that is height and the hydraulic radius. So the relation between H and R will tell you what kind of a bin you're looking at. So before we proceed with it, hydraulic radius is defined as D by 4, that is diameter of the silos divided by 4. So this is the formula for hydraulic radius of a cylindrical silo. So D by 4, which is given as 1.82 meters divided by 4, which is 0.455 meters. So this is your hydraulic radius. So the relation between your H and your R will tell you what kind of the bin it is. So if H is greater than 4 times of R, then you're dealing with a deep silo. That is, it has a very large height. If you're dealing with a shallow silos, your H will be less than 4R. So first, when you're dealing with design of silos, you need to calculate what is your H, what is your hydraulic radius, and you need to first figure out if it's a deep silo or a shallow silo. Based on that, your design formula will also change. So in this case, we calculated the hydraulic radius to be 0.455. So if you so 4 times of R is again 1.82 meters, which is less than your height. Your height is 20 meters, but your 4 times R is only 1.82 meters. So since height is greater than 4, much greater than 4R, we are dealing here with a deep silo. Based on that, our formula for calculating the vertical pressure will change. So I hope till this is clear, how to calculate the hydraulic radius and what to do to first figure out what kind of a bin we are dealing with. If there is any doubt, kindly let me know. Okay, so first we calculate the hydraulic radius, compare it with the height, and figure out what kind of a silo we are using. So in this case, we are looking at a deep silo. So for a deep silo where you have friction effects coming in, so when you're dealing with friction effects between the grains and between the silo and the grains, and you're dealing with a deep silo, in all these three conditions, we will use a design equation known as Janssen equation. So Janssen equation states that PL, which is the lateral pressure, is equal to WGR by mu into 1 minus E power minus K mu H by R. So here in this formula, W stands for the bulk density, G stands for the acceleration due to gravity, R stands for hydraulic radius, mu stands for the coefficient of friction between the grains and the walls, K here stands for the ratio of lateral to vertical pressure, and then mu again is the coefficient of friction. H is the depth of the grain. It is not the height of the silo, it is the height of the grain. So you will not fill your silo entirely up to 20 meters. You will have some head space also. So your H here is the depth of the grain and not the depth of the silo. So H is depth of the grain divided by R, which is again the hydraulic radius. So this is known as Janssen equation, which is followed when you are dealing with a deep silo and you have frictional effects also coming in. So we have all the parameters given in the question itself. We have the bulk density given. We calculated the hydraulic radius. The coefficient of friction mu is given in the question. K, that is the ratio of the lateral to the vertical pressure, is also given. The height or the depth of the grain is also given. So it is just plain substitution that we are looking at here. So substituting from what is given in the question, we have bulk density as 700 kg per meter cube, G as 9.81 meter per second square, R that we calculated, that is the hydraulic radius, as 0.455 meters, mu, that is the coefficient of friction, is given in the question as 0.42. And then in the second product term, we have 1 minus E power K, which is the ratio of lateral to vertical pressure, again given in the question as 0.33. Mu is again 0.42, and height of the grain, that is to which height we have filled up the grain in the silos, is 15.24, and then again hydraulic radius is 0.455. So this is just basic substitution that we are dealing with here. In case of any doubts, kindly let me know. We can repeat that part again. So on further simplifying, we get PL is equal to 7439.25, that is this term, into 1 minus E power minus 4.642. Basically, I just simplified the equation. I am just simplifying the calculation right now. And then we get PL as, that is the lateral pressure, as 7367.76 Newton per meter square. So this is the lateral pressure. But what is asked in the question is vertical pressure. So there are two kinds of pressure that we are dealing with in the grains. There is lateral pressure and then there is vertical pressure. So this is the formula for lateral pressure. So we have now calculated what is PL. We know the ratio of the lateral to vertical pressure given in the question as 0.33. So we know K, we know what is the lateral pressure. We can find out what is the vertical pressure from this relation. So given in the question itself, PL by PV is equal to 0.33. So we know PL from the calculation above. We know that that is equal to 0.33. From there, you just substitute it and you get PV as 22,326 Newton per meter square. In the question, it was asked what was the PV in kilonewton per meter square. So we convert Newton per meter square into kilonewton per meter square, which comes out to be 22.326 kilonewton per meter square. The answer to this question is option C. So this is the amount of pressure that your silo has to deal with. Accordingly, you will kind of change the material that is required for making the silos. If you know what kind of requirements you have, you can calculate what are the pressures that will be exerted on the silos. Accordingly, you can design your silo in such a way that it is able to withstand that pressure, withstand any changes in moisture content, withstand changes in temperature because of changing seasons. So all those you can calculate by calculating the pressure exerted by the contents inside the silos. So hope this is clear. If there's any doubt in any part of the question, kindly let me know. So just to give a recap, we calculate the hydraulic radius as d by 4. We compare the H and R to figure out what kind of a silo we are dealing with. In this case, it is a deep silo. Janssen equation is used for a deep silo. That is the only equation that is used for a deep silo, where you have frictional effects also coming in. You basically substitute, all the values are given in the question. You substitute and figure out what is the lateral pressure. We know the lateral pressure now. K is given in the question, which is the ratio of the lateral to the vertical pressure. So from there, you can calculate what is the vertical pressure. So that is what was asked in the question. That is what we have done. So answer is option C. Hope this is clear. So you need not worry about this. All the lectures will be made available, both the recordings as well as the slides will be made available. So you will have access to these questions anytime you want. So moving to question 3. Which of the following option shows the correct trend in terms of the decreasing oxidation potential? So you have 4 different molecules that you are looking at: ozone, peroxides, hyperchlorides, and free chlorines. Yeah, so the answer is option A. Ozone has the most oxidation potential, which is why it is often preferred now to use ozone to decrease any sort of infestation or so. So ozone followed by peroxides, hyperchlorides, and free chlorine. So ozone actually gives kind of a fresh kind of a smell, whereas the other chemicals will give you that kind of a chlorine smell or so, which is why it is not preferred also much in industrial use. But when we go strictly by oxidation potential alone, so ozone has the highest oxidation potential, followed by the peroxides, hyperchlorides, and then the free chlorine. So, answer is option A. Okay, so question 4. For a particular mass of grain stored in a bin, the angle of internal friction of the grain is 40 degrees. The ratio of the normal pressure to the applied pressure within the bin is dash. So again, when we are dealing with internal friction, we basically mean within the grains, there will be some sort of friction because of the sliding capability of grains. When you load the grains, it can slide, it can be, they are continuously in contact with each other. So there's kind of a shearing effect or a friction. So because of this friction, again, your pressure will also be influenced. So the angle of internal friction here of the grain is 40 degrees. Generally we consider that greater the angle, more is the flowability of the material. So the angle of internal friction is 40 degrees. The ratio of normal pressure to the applied pressure within the bin. Any clue how to solve this question? What is the relation between the ratio of normal pressure and the applied pressure? That is the same K that we dealt with in the previous question. The relationship between K and internal friction is what is asked in the question. So for the ratio of the normal to the applied pressure, which is K, is equal to 1 minus sine phi divided by 1 plus sine phi. So here phi is the angle of internal friction. So that is how your internal friction determines what is the ratio of the normal to applied pressure in a silo. So we just basically substitute 40 degrees here because that is the angle of internal friction given. So we substitute the values 1 minus sine 40 divided by 1 plus sine 40, and we calculate what is the ratio of normal to the applied pressure. So K is equal to 0.217. So if the ratio of the normal to applied pressure is not given in the question, you only have the internal friction, you can calculate the ratio and then move on to calculate what is the pressure, lateral pressure, what is the vertical pressure, and so on. So K in this question is 0.217. So answer is option A. Hope this is clear. So there are several sites in the internet also that basically gives you a proper thorough idea of each and every parameter that is involved in determining the silo design. So one of this is the angle of internal friction. There are bulk densities of the grain, the apparent density of the grain. So all temperature, everything will come into picture. There's a very thorough explanation and thorough blogs written on these, so you can go and refer to those as well. And in fact, majority of these questions are kind of adapted from those sites. Question 5. Match the functions of the biological nose given in column 1 with the similar functions operated by the e-nose components in column 2. So you have column 1, which is your biological nose function, which is inhaling mucus, olfactory epithelium and nerve impulses. In column 2, you have the components of the e-nose: filter, circuitry and neural network, pump and sensors. So answer C. So yeah, so inhaling, correct. Inhaling is linked with the pump of the e-nose. Mucus is linked to filter. So basically, what a mucus does in your nose is basically filtering all the dust particles and so before it reaches our lungs. So mucus is basically performing the same. Filter is basically performing the same functions as a mucus. Third is the epithelial olfactory epithelium, which has all your receptors and sensors that will detect your smells first. So the olfactory epithelium is basically made of receptors that detect the smells. So that is equivalent to the sensors in your e-nose components. And nerve impulses is equivalent to your circuitry and neural network. So e-nose, again to just summarize, inhaling is same as pump, mucus is the same as filter, the role of olfactory epithelium is done by sensors, and nerve impulses is done by circuitry and neural network. So the answer is option C. So e-nose components, e-nose is basically used to um, to replace human sniffers. So if you have any volatile compounds like coffee, you want to analyze some food product based on its smell, so instead of hiring human sniffers which have multiple other disadvantages as discussed in the lecture videos. So as discussed in lecture videos, you have disadvantages like, first thing is that human sniffers are extremely expensive and they cannot be used for inhaling toxic substances and so on. On the other hand, when you're dealing with biosensors of these sort, you have reproducibility, you have reliability, and you can have a wide range of compounds that you can be analyzing. That is the role of the e-nose basically. So question 6. In hyperspectral imaging equipment, dash allows only specific wavelengths corresponding to a particular image to be captured by the camera. So you have A, light source, B, imaging optics, C, imaging charge coupled device, and D, tunable filters. So hyperspectral imaging equipment is also used for analysis of your grains and so on. Yeah, so answer is D, tunable filters. So we're just discussing each and every component one by one, just a short description. So all the 4 components that is discussed here is a part of the hyperspectral imaging equipment. First is the light source. It basically illuminates the sample, and based on the kind of spectra that you want to take, you can either have white light for near infrared radiation, or you can have a different wavelength light based on the kind of illumination that you want for your sample. So white light can be used for near infrared spectrum and visible data collection, and specific wavelengths can be selected using filters. So then you have imaging optics that collects your sample reflectance and illumination wavelength. So you have multiple optics that are present inside your equipment that will help in the reflectance of your light that is coming in, and that will help it reach the detector as well. So imaging charge coupled device. Sorry, first we'll deal with tunable filters. So yeah, tunable filters is the answer to this question. This component allows only specific wavelengths corresponding to a particular image to be captured by the camera. And then is the imaging charge coupled device. It records the intensity of the individual pixels for each of the wavelength in the data collection range. So if you want only a certain wavelength, that will only be passed through the camera, and then it will record the intensity of each of those individual peaks of that particular wavelength. So all 4 of them are a part of the hyperspectral imaging equipment, where each of those have a different function. And tunable filters is the one that is responsible for allowing only specific wavelengths corresponding to a particular image to be captured by the camera. So answer is option D. Question 7. Which among the following step reduces the dimensionality of the measurement space in ENOS analysis? Have A. Pre-processing, B. Feature extraction, C. Classification, and D. Decision making. So which step is involved in reducing the dimensionality of the measurement space? So any clue what are the steps or involved in an ENOS analysis? What each of those steps signify? No, the answer is not C here. The answer is B in this case. So what happens is that basically your eNose, as we discussed before, it works very similar to your biological nose. And when you're dealing with an eNose analysis, there are 4 steps involved. First step is the pre-processing, where you'll have your sensory data, your data, everything collected, and you'll have a pre-processing where you'll collect all the features that you want to study. So pre-processing involves that, where you collect all your data from your sensors and then combine it and process it. Second is the feature extraction. So what happens is that in a feature extraction process, you'll collect so many features, because the ENOS is capable of collecting so many features when you're dealing with a sample. But you want to analyze only certain features. So based on that, if you have an idea as to what feature that you want, in this feature extraction step, like say if you have n features, you will reduce the amount of features that you want to analyze. So if you want only some kind of some volatile, if you're looking at some kind of a volatile substance or so on, and if you know what kind of feature you want from all this n number of features, you will select only that feature that you want. So basically you are reducing the dimensionality of the measurement space. It would have collected thousands and thousands of features, but you would want only certain 50 to 60 features, so you will collect only those. So in feature extraction step, it will reduce the dimensionality of the measurement space and extract only the useful information that you want. So that is what will happen in a feature extraction. And then comes classification and decision making. So in these stages, basically the ENOS will try to figure out from the extracted features what compound it is looking at. So in order for the ENOS to figure out what compound it is looking at, you should have already trained the ENOS with certain chemicals. So you will take up standards or so on, for which you know what the property is, what the purity is, and everything. So you take a known sample of known concentration, known purity, and known features and properties. With that, you will create a library. Basically, you will tell the ENOS that if this compound is present, this is the pattern that you will get. If this compound is present, that is the pattern that you will get. If the combination of these compounds are present, this is the pattern you will get. So basically, you will train the ENOS with known samples. Then you will expose the ENOS to your unknown sample. At that time, after your feature extraction is done, where you have collected only the useful information, that useful information will be compared with its database. That is your trained set. So that will be compared with the trained set, and it will figure out if this is corresponding to the compound that it already knows or not. So, or what is the combination of the compounds that is present. This it will calculate based on the data set that you trained it with. So basically, it will classify all the features that are very similar, and then it will make a decision as to what compound or what kind of volatiles, what is the concentration or so on it is dealing with. So that is what is involved in classification and decision making. It will classify the patterns according to very similarities and so on, and then those classes will be compared with its database, and then a decision will be made that this is the odor of some compound, or this is the quality of the compound, and this is how much it could be present in the sample. So that is what happens in all of the 4 steps. First is pre-processing, where you will have all your data collected from the sensors. Then you will have feature extraction, where you will extract only those features that you are interested in This will reduce the dimensionality of the measurement. If it collects 1000 data points, you might not require so much. You require only 100 data points, you will just extract those features alone. That will itself reduce your amount of measurement that you have taken. Then you will have classification, where you will separate it into classes and figure out patterns. That patterns you will compare with the database and then figure out what is the order or what is the sample that you are looking at. So this is the entire process of an ENOS. The answer is option B. So hope this is clear. Any doubts, kindly let me know. Okay, question 8. Which among the following option is showing the correct classification of spoilage according to the levels of carbon dioxide? So A, you have low level spoilage, which has a carbon dioxide levels of 0.08 to 0.1%. B, hotspots with carbon dioxide levels of 2 to 3%. Serious spoilage with CO2 levels less than 2%. And low level spoilage, that is from 0.8 to 1%. So what is the level of carbon dioxide, from where you will calculate what is the level of spoilage that has happened? Which one of these is correct? So before we proceed, the reason why we are measuring levels of carbon dioxide is because if there's any sort of infestation that is happening in your grains, any mold, any insects or anything, all those have a tendency, all those are organisms that respire. So it will take in oxygen and it will produce carbon dioxide. So if you have more and more infestations, or it means more amount of carbon dioxide is produced, hence more amount of spoilage is also happening. So basically your amount of carbon dioxide is directly proportional to the level of spoilage. Higher the amount of carbon dioxide produced, higher the amount of insects or microorganisms or fungus, and higher the amounts of spoilage. Higher the levels of that will generate the high levels of carbon dioxide. So there are generally 3 levels that are considered: low level spoilage, hotspots, and serious spoilage. So the levels that is generally agreed for low level spoilage is 0.08 to 0.1%. So if your carbon dioxide levels, you have sensors inside your silos. So if your carbon dioxide level in the silo is 0.08 to 0.1%, it means a low level spoilage. That is, you have lesser number of microorganisms or infestation. Serious spoilage is 2% or higher. 2% or higher levels of carbon dioxide. And hotspots, that is, you have large amount of infestation, or hotspots is 5 to 7% of carbon dioxide. So based on the carbon dioxide levels at different regions in the silo itself, you can figure out what part of the silo or which silo is most infested, which one is not. So the silos are inspected based on one of the parameters by which the silos are inspected is based on the carbon dioxide level. So only A is correct, the rest 3 are false. For hotspots, it is 5 to 7%, and for serious spoilage, it is greater than 2%. So hope this is clear. Moving to question 9. 2 tons of grain stored in a bin is cooled by aeration with ambient air at 30 degrees Celsius and at a volumetric flow rate of 0.22 meter cube per minute. So kindly ignore this ton. So the volumetric flow rate is 0.22 meter cube per minute. The specific volume of air at 30 degrees Celsius is 0.91 meter cube per kg. The specific heat of grain and air are 1.67 and 1 kilojoule per kg Kelvin respectively. Calculate the time required for cooling the grain in the bin. So when you will have your grains stored inside the bin for seasons and seasons. So when you have a summer season or so, you will have your grains will start heating up because of higher temperatures, higher atmospheric temperatures. Your grains will also start heating up, and when it reaches a certain temperature, it becomes very optimal for growth of microorganisms, fungus, and so on. So you need to make sure that the plus on top of that there could be also sprouting, all those undesirable changes. So in order to prevent all those, it is often preferred to maintain a certain temperature which is why we supply air inside the bins to cool down the grains. So in this case, we have the volumetric flow rate of the air that is supplied. We know the specific volume of the air. We know the specific heat or CP of the grain and air, and we need to calculate what is the time required to cool the grain inside the bin. So this is basic heat transfer equation that we have often discussed in the previous lectures. So first we look at the given. Given here is mass of the grain is, that is mg, is 2000 kgs. The volumetric flow rate is 0.22 meter cube per minute. Specific volume of air is 0.91 meter cube per kg. The Cp of grain is given as 1.61 kilojoule per kg Kelvin, and Cp of air is given as 1 kilojoule per kg Kelvin. So any clue how to proceed with the question? So in this case, we make an assumption that whatever heat transferred, whatever is the heat transferred from the grains, it is going on to whatever heat is transferred from the air, it is going to the grains. Sorry, the other way around. So the grains are hotter, so the whatever heat is transferred is present in the grains is transferred to the air, so that the grain starts cooling down. So this heat transfer happens without any loss. This is our assumption. The heat transfer rate from the grains is equal to the heat transfer rate to the air. That is, whatever heat is present in the grains is transferred to the air, thereby cooling the grains. So this heat transfer is equal. That is, there is no other loss present in the cooling process. So this is our first assumption that we are going to make. So in this case, you have, when you the heat transfer rate equation can be given as mCp delta T. The mCp delta T is basically your heat amount of heat that is generated, and divided by time will give you heat transfer rate. So the numerator is basically the amount of heat, divided by time will give you heat transfer rate. So the amount of heat for any particle that we are dealing with can be given as mCp delta T. So in this case, heat transfer from the grains is equal to mg, which is the mass of the grains, cpg, which is the Cp of the grains, and delta T divided by time, small t. That is equal to heat transfer to the air. So ma, which is the mass of the air, Cpa, which is the specific heat of the air, delta T divided by time. So this is equal. We already have mg, we have the Cp of the grains, delta T will be the same for both. So basically, after a long time, when it is close to completing the process, your delta T will be the same for both. So you can actually cancel delta T and delta T here, but we will discuss that later. So first we have mg, we have cpg, we have cpa, we need to calculate what is ma. So the mass of the air can be calculated from the volumetric flow rate and the specific volume given in the question. So the mass flow rate of air, ma by t, this is actually ma by t. Mass flow rate of air, ma by t, is equal to volumetric flow rate divided by specific volume. So this is in meter cube per minute. This will be in kg per meter cube, sorry, meter cube per kg. So when you divide both of those, you will get the mass flow rate in the units of kg per minute. This is how you calculate the mass flow rate, which is ma by t. So you know what is the volumetric flow rate of the air. To know the specific volume, all we need to do is substitute it. So ma by t is equal to 0.22, which is your volumetric flow rate, divided by 0.91, which is your specific volume. This, when you divide, it gives you 0.241 kg per minute. So this is the mass flow rate of air. This ma by t you can substitute in the first equation, where you are equating the two heat transfers. So ma by t is something you can substitute here back. So mg is given as 2000 kgs in the question. Cpg is given as 1.67 kilojoule per kg Kelvin. Delta T we still don't know, and time is what we need to calculate. That is equal to ma by t, which is 0.241 kg per minute. Cpa is given at 1 kilojoule per kg Kelvin, and you have delta T. So delta T gets cancelled. and you can calculate what is the time taken for the cooling process. So if you calculate from there, you get time is equal to 13,916.67 minutes. And since it is asked in hours, the question is asked in hours, when you convert it into hours, it comes out to be 231.95 hours. So any doubt in this so far? Any doubt in the procedure that needs to be repeated? Basically, you're assuming no loss of heat. You're equating the heat transferred from the grains to equal to the heat transfer to the air. So that is done by the formula mCp delta T divided by time. That will give you the rate. You can calculate the rate of mass, the mass flow rate of air by the volumetric flow rate and the specific volume. That will give you Ma by T. Rest all are given in the question. Delta T gets cancelled because it's the same. Irrespective of what the other temperature is, it's going to be the same because there is no other heat loss. So from there you can calculate the time required for the cooling process. Answer is D. Hope this is clear. If there is any doubt, kindly let me know. We can repeat the question as well. Okay, so moving to the next question. Question 10. The condition of the cell membranes of the stored seeds is measured by which of the following parameters? A. Fat acidity value, B. Headspace condensation, C. Electrical conductivity, and D. Seed germination. So the condition of the cell membrane is not calculated through seed germination. It is calculated through electrical conductivity. So we'll discuss each of these one by one. So the fat acidity value, which is FAV, is the measure of chemical changes occurring within the deteriorating seeds. So the seeds that are no longer fine, that keep degrading or so, will have a change in its fat acidity value. That is, the chemical components inside your seed will start changing as it starts degrading or destroying. So these chemical changes can be calculated from a parameter known as fat acidity value. So this is one of the methods to figure out if the seed is fine or not. The other one is the electrical conductivity, that will tell you the condition of the cell membranes of the seeds. So generally cell membranes have a certain conductivity when they are intact. So based on the electrical conductivity of the cell membrane, there is a difference between when cell membrane is intact and when it is ruptured. So based on this difference in the electrical conductivity, you can figure out if the cell membranes of the seeds are intact or not. So electrical conductivity is the one that is used to measure the condition of the cell membrane of the stored seeds. The headspace condensation, basically if you have a lot of moisture in your grains, or if there is too much of growth as well, so because of those growth and everything, you will often have headspace condensation. That is, if you have a big bin or a silo, you will have, if it is of 20 meters, you will fill only 15 meters with grain. Rest of the 5 meter will just be air. So if you have too much of growth of the microorganisms, that will result in respiration processes and other metabolic processes. And because of these metabolic processes and so on, and in addition to that, because of the moisture that is present in the, too much moisture that is present in the seeds, you will have something known as the headspace condensation. That is, the region above your seeds will have condensation droplets in it. So based on that headspace condensation, you can have an idea of how much a grain has been spoiled. So the lesser the condensation, better it is, because you will know that your seeds are dry and have not been subjected to any sort of spoilage. So headspace condensation is used to measure or detect the grain spoilage. And sprouted grains also indicate poor air circulation in the bins or leaking roofs. So if you have leaking roofs or poor air circulation, you will have water trickling in, you will have changes in temperature, you will have you won't be able to maintain the temperature that is required to make sure that the grains do not sprout. If you have all these leaks and everything and poor air circulation, then the grains will not be cooled down, it will not be maintained at the desired level. If that is the case, then it will start sprouting. So the seed germination is an indication of the poor air circulation in the bins and the leaking roofs. If you have leaking roofs, you will have water going inside. Because of poor air circulation, it will be pretty warm inside the bin. If it has water and if it has warmth, then the grains will start sprouting. So this is also indicative of a poor silo design. The answer is option C. It is electrical conductivity. The difference between an intact membrane and your ruptured membrane is what will give you the condition of the cell membranes of the seeds. So hope this is clear. These are just some of the parameters that is used to calculate, analyze whether your seeds are of good quality right now or not. So question 11. Which among the following is a chemometric classification as well as regression analysis applied for hyperspectral image analysis? So you have artificial neural network, support vector machines, C individual component analysis, and D convolution neural networks. So in hyperspectral image analysis, you will have so much data, you will have something known as a data cube. So based on that data cube will have so much amount of data, that is whether or not your seeds are intact, whether they are hollow. Just a minute. So whether they are hollow, whether they are infested, whether they are starting to decay, all those information will be given in the form of a data cube, a colored data cube rather. So it will be literally in a cube shape format, where each of the layers will have colors that will give you information regarding the quality of the food product that you are looking at. But since they are you're dealing with a very complex and too much data and all, you require certain specialized softwares to perform this analysis. So be it the chemometric classification of figuring out which component is what, which compound is what are we looking at, or we are dealing with regression analysis for comparison purposes, you require certain specific softwares for these softwares, or rather techniques, to identify what is the information that the data is giving. So for that, there are multiple techniques involved, out of which one of these is involved both in chemometric classification, that is to identify what class or what kind of properties that the sample has, and then on top of that you have regression analysis also to figure out if how accurate the results are. So for both of those, for each of those you have separate softwares also, and some of them have both features as well. So artificial neural network and support vector machines are regression analysis methods used in HSA analysis, that is hyperspectral image analysis. And classification method of chemometrics include principal component analysis, individual component analysis, k-mean cluster analysis, genetic algorithm, convolution neural network, support vector machine, and partial least square discrimination analysis. So all these, the what it does is not, I don't think it is important for you, but it is best to know what methods come under what classification. So it is, when you compare these both, only support vector machine has the ability for both regression analysis as well as classification. The rest of those are specialized for only one of the method. One of the function. So the answer is option B here, support vector machine. So more about this is given in the lecture videos as well, but this is not something that needs to be known on a detailed basis also. So moving to question 12. For aeration cooling, the rate of air flow inside the bin required is A 1 to 5 liter per second, 5 to 10, 0.5 to 1, and 10 to 20. So which is the flow rate that is optimum for an aeration based cooling? So there are generally what happens is when you're storing your grains in a silo, you'll often ensure that there is air circulation inside. And based on what is your requirement, your flow rate of your air that you're supplying inside the silo will also change. So there are multiple functions of supplying air. Sorry, first is the aeration maintenance. So using aeration to protect the grain quality and prevent temperature increases. So if you maintain that sort of aeration where you are protecting the grain quality, you require very minimal amount of air, which is 0.5 to 1 liter per second of airflow. So for aeration maintenance, this is the amount of flow rate that requires. When you're dealing with aeration cooling, where you have very hot temperatures outside, and you need to make sure that your grain is not getting overheated, or in order to make sure that it's not too much infestation also, you require the bin to be maintained at a certain temperature. So this temperature requires air supply to cool the grains down. So you have aeration cooling that is involved. That for that you require 1 to 5 liters per second of flow rate. And when you want to dry, when you want to remove or strip off all the moisture from the grain, you need a much more stronger flow of air, which is 5 to 20 liters per second. So these are the three main role of supplying air inside the silo. First is to maintain the aeration to ensure that the grain quality is protected. Second, to ensure that the temperature is maintained and you do not cause any growth of insects or so on. And then you have aeration drying as well to remove off all the moisture from the grain. The answer to this question is option A. Okay, so question 13. For an air flow rate of 2 meter cube per minute, the linear air velocity in the intergranular space in a circular storage bin having 2 meter diameter and 0.4 void fractions will be dash meter per second. So when you have a bin or some a storage bin and you have grains loaded into the bin, you will have small air pockets between the two grains. So when you supply air, that air will pass through these small air pockets only. So when given the flow rate of the air and given the void fraction, that is between the two, the volume of the void between the grains is the void fraction. So assuming the grains to be spherical in nature, if you just arrange all the spherical particles, you will have small gaps between two spheres. So all of those regions are your voids, and void fraction means the total amount of empty pockets present when compared to the total volume. So that is your void fraction. We need to figure out what is the linear air velocity in the intergranular space, that is between the two grains, or basically in the void region. What is the air velocity is the question. So any clue how to proceed with this? How do you, from the flow rate, how do you calculate the velocity? And from that, how do you calculate the velocity on the intergranular space alone? So when you want to convert flow rate into velocity, you divide it by the cross-sectional area through which your air is flowing. Let's say the air is going from the base of the bin. So given here is volumetric flow rate is 2 meter cube per minute. The diameter of the storage bin is 2 meters. The void fraction is 0.4. So for interstitial velocity, that is the velocity between the two grains, that is the intergranular space, or the interstitial velocity can be given by volumetric flow rate divided by cross-sectional area into void fraction. So volumetric flow rate divided by cross-sectional area will give you the normal velocity. That into the void fraction will give you the intergranular space alone. That is the velocity through the intergranular space alone. So interstitial velocity can be given as volumetric flow rate divided by cross-sectional area of the bin is pi by 4 into d square, where d is the diameter of the storage bin. So pi by 4 into d square is a cross-sectional area. That area into the void fraction will tell you what is the area between the two grains. So the volumetric flow rate divided by that area between the two grains will give you interstitial velocity. Hope this is clear. If there is any doubt, kindly let me know. We can repeat the question. So when you substitute the values, you get 2 meter cube per minute, pi by 4 into d square, which is 2 meters again. So 2 square, and void fraction is given as 0.4. This is just basic substitution here in this question. So simplifying it, that is equal to 2 divided by 3.14 into 0.4, and you get your interstitial velocity as 1.59 into meter per minute. So this is in meter per minute. We have to convert it into meter per second. So that is equal to 0.0265 meter per second. Answer is option D. So hope this is clear how to calculate the interstitial velocity between the two grains, given that you have the void fraction between the grains. Okay, so moving to question 14. Which among the following is not a common moisture proofing material for storage of grains? A. Aluminium foil, B. Asphalt, C. Foam polystyrene, and D. Polyethylene. So which among these four is not used as a moisture proofing material? No, asphalt is actually used as a common moisture proofing material. The answer here is option C. So aluminum foil, asphalt, and polyethylene, these are all very common coatings or substances that are added in the storage bins that will act as a moisture proofing material. Whereas foam polystyrene is more of an insulation material, that is to prevent any fluctuations in temperature. That is why foam polystyrene or glass wool is added. So these two do not work as a moisture proofing material, they work as an insulating material in the storage system. Whereas the rest three, the aluminum foil, asphalt, and polyethylene, are used as moisture proofing material in storage bins. The answer is option C. Based on the kind of bins we are looking at, also the thickness of the proofing material that you give will also change. Question 15. The phenomena that moisture moves in the same direction as heat flows is known as A. Moisture migration, B. Thermo-moisture conductivity, C. Thermo-moisture diffusivity, and D. None of the above. So which one of this is correct? No, it's not moisture migration, because moisture migration need not be necessarily linked to the direction of the heat flow. So it is the thermo-moisture conductivity concept, where your moisture moves in the same direction as your heat flow. So that is known as thermo-moisture conductivity. So we will discuss more in the coming up question as to why you have this moisture migration and so on with the heat flow. So in this particular question, the answer is option B. We will look into it in a little more detail in the coming questions. Okay, so this is again one of the design, silo design question. The wheat weighing 900 kg per meter cube is loaded in a circular concrete silo of 3 meter internal diameter and a clear height of 8 meters. The angle of internal friction for wheat is 25 degrees, and that for the wheat and the concrete is 24 degrees. So here you do not have the coefficient of friction. In the first question, the coefficient of friction was given, and for the wheat and the concrete, that is between your grains and your silo, the coefficient of friction was given, but in this case you are given only the internal friction angle. The angle of internal friction for wheat is 25 degrees. That is between the two grains it is 25 degrees. Between the grain and the bin is 24 degrees. Applying Airy theory, calculate the maximum lateral pressure at the bottom of the bin section. So in this question, they have already given you what formula or what you need to apply. Had it not been given, then you will figure out again what is the kind of silo that you are looking at, then choose an appropriate formula. In this particular question, they have already asked you to apply the Airy theory, so we'll proceed with that. So before we discuss the Airy theory, given in this question, density of the wheat is 900 kg per meter cube, diameter of the silo is 3 meters, height is 8 meters, the angle of internal friction between the grains is 5, which is equal to 25 degrees, and the angle between the wheat and the bin or the concrete is 5 dash, which is 24. So in Airy theory, this will consider both the internal friction between your wheat and your wheat as well as the concrete. So Airy theory can be given as, again, the lateral pressure PL is equal to WH into 1 divided by root of mu into mu plus mu dash plus root of 1 plus mu square the whole square. So here in this case, W stands for density of the wheat, H stands for height of the silos, mu stands for your coefficient of friction between the grains, mu dash stands for coefficient of friction between the grain and the bin. So we have only the internal friction angle. We still do not know what is the coefficient of friction between the grains and between the grain and the bin. So that is something we need to calculate. After we calculate that, we can just directly substitute it in the formula. So where mu is equal to, the definition of coefficient of friction is mu is equal to tan into internal friction angle. So if you are looking at coefficient of friction between the grains, you have mu is equal to tan phi. If you are looking at the coefficient of friction between the grain and the wall, then that is mu dash is equal to tan phi dash. So the tangent of the internal friction angle will give you coefficient of friction. This is the common definition of coefficient of friction. So we already know what is phi, we know what is phi dash. From there we can calculate what is mu and what is mu dash. So mu is equal to tan of 25 degrees, which is 0.466, and mu dash is tan 24, which is 0.445. So this again, you know now the coefficient of friction between the grains and between the grain and the bin. This you will substitute inside this equation to calculate what is the lateral pressure at the bottom of the bin section. So PL is equal to, substituting the values, 900 kg per meter cube into 8 meters, which is the height of the contents present, into 1 divided by root of 0.466, which is your coefficient of friction between the grains, that is mu, and mu dash, which is the coefficient of friction between the grain and the bin. So mu plus mu dash plus 1 plus mu square. I just basically substituted the mu and mu dash into this equation. I hope till here it is clear. So this is the formula for Airy theory. The previous question we were looking at Janssen equation because we weren't specified what technique to use. So we went forward with designing first if it is a deep silo or a shallow silo. Then we started considering the friction effects, and then we came down to Janssen equation. Here it is already given, it is already asked of us to use the Airy theory, so we will directly use this formula. So substituting the values, we have to further simplify this. This is equal to 900 into 8, which is 7200, into 1 divided by root of 0.466 into 0.466 plus 0.445 plus root of 1 plus 0.466 the whole square. When you simplify this again, you get the lateral pressure as 2338.16 kg per meter square. So this is what is asked in the question. If you had what is the K given in the question, then you can calculate what is the vertical pressure as well, similar to the previous question that we discussed. So hope this is clear. This is the formula for Airy theory. This is basic substitution involved here. So this is again one of the design theories for a silo. One is the Janssen equation, second is the Airy theory. If you guys have any doubts, kindly let me know. We can repeat the question again as well. The moisture accumulation during summer due to moisture migration will be expected at the dash of the bin. A lower portion, B upper portion, C near the walls, D near the center. So in summer season, where do you expect to see most of the moisture in a silo bin? It's not upper portion. Upper portion is during the winters. In winters, moisture is present in the upper portion, whereas in case of summers, it is present in the lower portion. So I'll discuss what is happening here. So let's say you had your grains present inside the silo bin, and now the season is changing from winter to summer. So when the season changes from winter to summer, your grains are still pretty cold, whereas your outer environment is slowly heating up because the season is changing. That is because of the summer season. So your atmospheric temperature is hot, whereas your inside your grains are cool. In that case, what happens is, as your temperature at the atmosphere starts rising, the first thing that starts heating up is your surface air. So this particular area will start heating up, whereas the bulk, that is the depth of your grains, will still be cold. So this is the first thing that heats up. The innermost, the core region of your silo will still be cold. So you have a heat up air here, you have a cold region here. So automatically heat will flow from a hotter region to a colder region. So what will happen is, your air will start moving to the center of the bin, and then will go towards the walls of the bin and then go up again. So this is the clockwise motion of the air that you will see. Because this region is still cold, this is the region that starts heating up. So air will start going on through this way. So air will start circulating like this. So what will happen is, as your air is circulating out, the hot air is being circulated, it will start taking off moisture along with it. As it goes from the upper region to the lower region, it will start collecting moisture as it is traveling. So this moisture containing hot air, as it reaches the lowermost region of the silo, this will still be cold, which is why you are having a heat transfer in the first place. So majority of the heat will be here, this will still be cold. So the moment the moment air with moisture reaches the colder region, all the water vapor will start condensing in this region, and this is where majority of the moisture will start collecting. So in a summer season, it is the bottommost part that has majority of the moisture present. So hope this is clear. First, all your grains will be cold because of the initial winter season. As the summer sets in, your atmosphere starts to heat up, atmospheric temperature rises up. That will heat first the surface of the grains, whereas the bulk region will still be cold. So this is hot, this is cold. So air will start moving in from hotter to colder region, and then will go again towards the walls of the bin and start rising up. So you'll have a circular clockwise motion. And as this motion is happening, your air will start collecting all the moisture from the upper regions, and as it reaches the colder region, everything will start condensing and your moisture will start collecting in this particular region. This happens in a summer season. So the answer is lower portion. Whereas in case of a winter season, the exact opposite happens. In case of a winter just now your summer has been over. So all your grains will be hot. Whereas your atmosphere will be cold. So this is hot, this is cold. So the first thing that will start cooling again will be your surface. So this is the first region that will start cooling, whereas this bulk region will still be hot. So whatever air is being circulated will pass from the hotter region to a colder region. So now it will go in anti-clockwise direction. It will go from the bulk, it will reach the cold surface, and then it will come down again to the through the near the walls of the bin, and then it will again go to the core of the bin. So you have an anti-clockwise motion here. So what happens in this case is, when your hot air from the bulk of the grain starts to rise up, so this region is becoming cold because of the winter season. So this is the first region that becomes cold. So again your hot air, which has all the moisture that was stripped off, will reach the cold surface and it will start condensing and it will collect moisture here. So in case of winter, the moisture will get collected at the top, whereas in case of the summer, moisture will be collected at the bottom. All because of this moisture migration, because you have a difference in your temperatures within the bin. In case of summer, your surface will be hot, bulk will be cold. So wherever is a cold region is where your moisture will accumulate. So since your bulk region is cold, you will have moisture accumulating at the bottommost region in case of summer. Whereas in case of winter, your surface will be cold, whereas your bulk will still be hot. So whatever moisture is there will be collected at the surface or the topmost region. So hope this is clear as to why there is a difference in case of the moisture collection during the winter and summer season. If there is any doubts, if any part of this has to be repeated, kindly let me know. So question 18. A cylindrical silo of 2.5 meter diameter and 20 meter height is filled with wheat. Calculate the height of the upper cone of the stored wheat if the minimum and maximum angle of internal friction are given by 25 degrees and 30 degrees respectively. The maximum angle of friction on a smooth sheeting is 18 degrees and the angle of repose is 25 degrees. So basically you have a cylindrical silo, where when you load the wheat, it forms a conical shape. So you already know the diameter of this cone, which is 2.5 meters, but you need to know till what height you filled up the wheat. So with this particular graph, can you figure out how to calculate the height of the wheat? So this is basically a cone. If you consider this as this is actually considered as the angle of repose. That is your angle made by the slanting surface of the cone to your radius. So this angle between the slanting surface and the radius is known as the angle of repose. So you know the radius, you know the angle, you can calculate the height from that. It's basic trigonometry only. So all these other variables are just there to confuse you. This is not relevant to the question. You can calculate the height if you're dealing with a proper cone here. You can calculate the height of the wheat that you added with the angle of repose alone. So height of the upper cone is equal to, which is equal to z, that is this is z, is equal to r tan theta, where theta is the angle of internal friction or the angle of repose. So in a conical region, the angle of internal friction is equal to the angle of repose. As you can see here, the minimum angle of internal friction is equal to the angle of repose. So if you take a tan of this angle, that will give you r by h. H by r, sorry, my bad. So the tan of this angle will give you h by r. You know the angle, you can calculate the tan of that angle. You know the radius, you can calculate the height from that. So the angle of internal friction is equivalent to the angle of repose, and from the angle of repose itself you can calculate what is the height. So r is 1.25 meters and your angle of repose is 25 degrees. So 1.25 meters into 25 degrees, so tan 25 will give you the height, which is your 0.582 meters. So this is the height of the wheat that was deposited or loaded inside the silo. Any doubt in this? So answer is option B. So we are calculating this because it is given that there is a cone kind of a shape formed upon loading the wheat. That is why this angle of repose is coming into picture here. I hope this is clear. Any doubts? Okay, question 19. The flow function in a grain storage bin is given as the ratio of A. Unconfined yield pressure of a solid to the consolidated pressure. B. Angle of repose of the solid to the angle of the internal friction. C. Hopper angle to the angle of repose, and Hopper angle to the angle of internal friction. So the flow function is kind of a parameter that tells you the flowability of the material. So when you're dealing with powders or when you're dealing with small grains, how easily it is able to flow can be calculated from the flow function. So the flow function is defined as one of the following of these options. What is the answer to this question? Any idea? No, that is not the answer. Hopper angle to the angle of internal friction is not the flow function. So the flow function or flow function is the ratio of unconfined yield pressure of a solid. So unconfined yield pressure of a solid means you are not enclosing the solid in any kind of a um, container or anything. It is basically unconfined. In that particular state, what is the pressure where it starts shearing, where it starts causing a shearing effect? So that is the unconfined yield pressure, or this, that is the unconfined yield pressure. Basically, you have an unconfined solid. In this particular concept, it is the unconfined grains. So grains are not kept in any kind of a container or anything. It is just unconfined. And when you apply pressure, what is the pressure required to start causing the shearing effect in an unconfined grains is your unconfined yield pressure. So this gives you some idea of the cohesive forces in your grains. And your consolidation pressure is basically your compressive pressure. Basically, when you start compressing your grains, all your air pockets will start reducing. The air pockets between your grains will start reducing, and you'll have a reduction in volume also. So this is because of the consolidation pressure. So the ratio between these two pressures will give you something known as the flow function. And based on the value of this flow function, you can have an idea of how easily flowable your grains are. So higher the flow function, higher the flowability of the, or more easily it flows. So if your flow function is higher, that is greater than 4, between 4 and 10, it means that the material can be easily flown. If it is close to 0 or close to, it's very close, less, then it means it's a pretty rigid grain and it cannot be, it does not have a flowing property when you load it inside a container or so. So flowability of the grain or any powder particles also is given by this flow function, which is equal to the ratio of the confined yield pressure to the consolidated pressure. Consolidated pressure is an indicator of the compressive force. Unconfined yield pressure is basically gives an idea of the cohesive forces. The answer is option A. And higher the flow function, higher the flowability of the material. Question 20. In the Pusa bin, the thickness of the PE sheet used to prevent moisture entry into the grain is 25 gauge, 250 gauge, 450 gauge and 700 gauge. So you have Pusa bin is basically your traditional storage facility, except that now you will have a certain thickness of polyethylene sheets that is coated onto the all the walls and the ceiling to prevent any moisture entry. So that thickness should be of a certain value for a Pusa bin. So which among these is correct for the Pusa bin? So in case of Pusa bin, we are using a thickness of 250 gauge of PE sheet. PE sheet, as we discussed in the one of the previous slides, polyethylene is one of the commonly used moisture removal material, coating material. So you coat the walls of the pusa bin with these polyethylene coating to prevent any moisture entry into the grain slows. So that is 250 gauge. The answer is option B. So with that, we conclude uh, this particular week's problem solving session. If you guys have any doubts, kindly let me know right now, or you can post it in the discussion forum or mail me as well. We can take up that question either now or in the later classes as well.